Hello friends, welcome to Architect Interview Question Series by Knowledge Powerhouse. And in this series, we are covering questions on system design, software architecture, design patterns. And these are like pretty good concepts to learn even for your day-to-day life, where you are working in your office and you want to apply these principles or concepts. Let's go on to our next question. Question is, what are the different types of design patterns in OOPS? So in object-oriented programming, we have some design patterns, and these design patterns are well-defined ways to solve some kind of a problems. And design patterns occur in like not only object-oriented programming, but also in different programming streams. But now in this question, we are focusing more on the design patterns of object-oriented programming only. So in object-oriented programming, we have mainly three categories of design patterns. First is creational. These are the patterns which are used for creating different kind of objects, classes, or entities. Then we have structural design patterns. This category of patterns are used to build the overall architecture. So in your architecture, you have different kind of structure. Like if you see a physical architecture, you have kind of a bridge, right? Whenever you have like two different roads that you want to connect, or you have like some kind of a facade. So similarly in object-oriented also use structural design patterns. And third category is behavioral one, which is like based on the behavior, the state of the software, how it can work in different kind of conditions. So those are the behavioral design patterns. Let's go into detail of each of these categories and learn about some of these patterns in detail. So in creational design patterns, some of the popular design patterns are builder, factory method, abstract factory, object pool, singleton, and prototype. So these are like seven main methods, design patterns. Let's go on to each of them. So in builder design pattern, we have like some kind of a flexible solution that can provide our problem of creating an object. So if you want to create an object, then you can use builder design pattern. And the intent here is to separate the construction of a complex object from its representation. Like, I mean, you actually are getting an object and you can start working on it. But before you get it, you have to build it. Let's say, I mean, you get a cup of coffee. So to get that cup of coffee, there is a complexity involved in building it. Like you need to add sugar, you need to add cream, you need to add which type of cream to be added, what temperature it has to be boiled to, and what kind of coffee, what kind of brewing is required. So all the things are taken in the case of building that coffee, and later on you can use it, right? So builder design pattern solves certain problems. First problem it can solve is that how can a class create different representations of a complex object? Like how can you create different kinds of coffee, right? I mean, if you have to create latte with like milk, or cappuccino with like soy milk, or with coconut milk, so all these kind of different objects can be built using builder pattern, and then the user can start using it, right? Another problem that builder design pattern solves is how can a class include creation of a complex object in a simple way, right? I mean, if you want to create the object in a simple way, how we can provide that to a calling class, client can see. Like if you see in this example, there is a director, and then in the builder we have a generic method called build part, right? And in the builder you have a concrete builder. So that concrete builder is the one where we like actually implement the build part, and there can be multiple build parts, right? Like let's say in case of coffee, you are like adding milk, adding sugar, adding so you can keep on adding all those things, right? And finally, when you call the get results, then you will get the actual product, and that product is returned back to the director. So that way the builder design pattern works. Another popular design pattern in the creational one is factory method. In factory method, we try to solve the problem of creating objects without specifying the class of that object, because like clients, they may not know like what class they are going to get, so they can just be given an interface that this is the kind of object you're getting, but the actual product will be different, which is dependent on the factory that we are using at that time. So this is done by creating objects by calling a factory method. and this is especially specified in an interface, and like it can be implemented in a base class and it can be overridden by derived classes. Like in this example, the creator has a like interface product. Now the actual creator one will call the factory method, right? And factory method will instantiate the actual product, which is product one, that will be created based on the conditions of the factory, and then that product is returned to the creator. So creator doesn't know the real product till the time of creation. All it knows is that it expects some product of type product, right? Like product one is of like an instance, is a like is a subtype of product, right? So that way the concrete product is given at the end, but initially all you need to know is that interface of that. Another design pattern is singleton design pattern, and this is more like an anti-pattern also. In this singleton, we restrict the instantiation of a class to one single instance. So in the whole system, you will only have single instance of this class. It is very useful when we need one object to coordinate across different systems. Like overall system needs one object to coordinate, then we create a singleton. And singleton will solve certain problems like that, how we can ensure that class is only one instance, and how we can ensure that only one instance is accessed easily, and how we can control the instantiation of the class. Like we don't want others to create instances, multiple instances of this class, and that can be restricted by singleton design pattern. And one more design pattern we want to cover in this is prototype design pattern. This is also creational design pattern. Here, like we use it to create the objects, and they are determined by prototypical instance. Now this is like clients, they have to clone to produce new objects. This pattern is used for avoiding subclasses of an object creator in the client application, like factory method does. So it avoids the inherent cost of creating new objects. It can just create a new object by using clone. So you don't need to do new to create an object. You just have a prototype, right, which is like original. Now what you do is that you do prototype.clone, and that will create like another instance for you. So based on that, if you have to do new, it might be very expensive to create that object, whereas using a clone is much cheaper and lesser intensive on your resources. And it will solve the problems like how can we create an object so that the objects can be specified at runtime. Like we can just say that this is the more objects we want to create, use clone, and it will create a copies of that. And how we can dynamically load these classes in our system, like that also is a problem that is solved by. So if you see this UML diagram, here the client class is requesting for a product, and that product is like not instantiated by product one, right? So instead the client will refer to prototype, and the prototype interface is having a method to clone. Now prototype is subclass, implemented by concrete prototype 1 and concrete prototype 2. So we have two copies of two different kinds of prototypes in our system, which are the concrete prototypes. Now the client class needs a copy of that. So what they do is that they just call clone to create it. So once they get the clone, then they will get the object, and that will be the one they can start using because it's a copy of the original object. The next category of design patterns is structural design patterns. Here we have popular design patterns like adapter, bridge, facade, decorator, composite, flyweight, and proxy. So if you see the diagram, this is the structure is being used to create the structure, like not to create one object, but to create the structure. Like if here we are creating a kind of a pyramid, so we can use a specific form in which this pyramid can be created by actual objects. So objects are already created by using creational pattern. Now here we are creating the different elements of the structure. So let's understand adapter design pattern. In this adapter design pattern, we have a alternating, we also call it as a wrapper design pattern. And what this pattern does is that it allows us to use an interface of an existing class and adapt it to the work with another class, so that we can two classes can work with each other. Mainly it is used to make existing classes work with other classes without modifying their source code. So, I mean, if you see an example where you have document object model DOM of an XML document, and then you can use it to convert it into different kind of interfaces as a class so that people can work with the DOM model. So adapter model solves problems like how can a class be reused that does not have an interface that a client requires. Like, I mean, client requires a specific class or specific interface, but your original class doesn't have it. Now you can create an adapter class that will convert that will translate the class into the kind of an interface that the client requires. If you see this example, you have a client, and then your client is calling to a target interface, and that target interface goes through like adapter, and then adapter is providing the interface to client, right? And an adapter is adapting to the adaptive, which is like your own class. So your own class doesn't match what client requires, right? It has the capability, but the interface doesn't match. So using an adapter, you can convert that interface according to the client. Now in future, if anything changes to the interface, then you only need to change the specific interface, not your original class. That is the help we get from adapter design pattern. So your original class can remain same, only the adapter needs to keep changing. Another design pattern is bridge design pattern, and it's also like used in software engineering to decouple an abstraction from the implementation. It looks similar to the adapter, but it's a little bit like there is minor differences between this. So here we use encapsulation, aggregation, and even inheritance to separate the responsibilities into different classes. So the problems that bridge design patterns solve are that we have an abstraction and its implementation, and both of these things should be defined and extended independently from each other. Like from an abstraction in this diagram, we extend it to another abstraction, and then from implementer, like we have another implementation. So that way the abstraction and implementation can be inherited. So if you see in this diagram, the abstraction isn't implemented as usual in single inheritance hierarchy. There is one hierarchy for an abstraction and the other is for implementer, right? That way we can use it. Then we have facade design pattern, and again facade is also similar to adapter. Here client wants to access our multiple classes instead of one class. In adapter normally is for one class. In this case, the client wants to access methods in multiple classes. Now what we do is that we create a facade. Using that facade, we expose the methods of the underlying classes, right? So that way client doesn't need to deal with our internal classes, our internal subsystem. They just need to work with one facade class, and that is the one will give them interface to multiple classes, right? So facade can improve the readability and usability of our software library, and it can mask the interaction with more complex components behind a single API. So we can just create a single API, and that is the one we can give it to the client, whereas that API behind the scene is served by multiple classes. So Facade solves a problem like to make a complex system easier to use and provide a simpler interface, and it also solves the problem of dependencies like that the client has on the subsystem. Now the client has dependency only on the facade, right? It doesn't have dependency on all the other classes of that subsystem. So these are the problems that facade design pattern solves. So adapter design pattern we already covered, and then we have composite design pattern. In composite design pattern, we try to describe a group of objects that have to be treated the same way as a single instance of the same type of object. So the intent here is to compose objects into tree structure so that they can represent the part or whole hierarchy. I mean, in this case, if you have a leaf, I mean, you have a component and then you have a leaf, right? And then leaf, or it can be a composite again. Right? So you can have, if you see, like a component under a component under a component kind of a thing. So I mean, basically the component can end in a leaf or it can end into a sub-component kind of a thing. So that way collection of that can form a overall composite object. Like, I mean, if you have popular example in an organization, you have like a CEO, and under CEO is a manager, and then under CEO an employee also. Under CEO we have more people who are like in next level, like VPs or senior VPs. They also are managers as well as they are employees. So that way, using that, we can have the whole system can be created by the parts as well as like by the whole composite also. So that forms like a basis of composite design pattern. Now, next set of design patterns are behavioral design patterns. In behavioral, we have command, iterator, chain of responsibility, observer, state, strategy, mediator, interpreter, all these design patterns. So in command design pattern, what we do is that we encapsulate all the information needed to perform an action or trigger an event at a later time. So this information includes the method name and the object that owns the method and values for the method parameters. For example, like, I mean, if you have a kind of a remote, right? In the remote, we can use a command design pattern. Like in remote, you just have some buttons, right? But each button is a different command, right? And those commands are actually methods that are like like increasing the brightness of your TV, increasing the volume of your TV, right? So all those are different methods that are invoked by calling those buttons. And then when you have those buttons, then you can even combine those commands to form a complex command, or you can have an undo kind of a thing. You can go back. I mean, all those things can be done. So as long as we have commands mapped to some kind of methods, you can make use of this. So with command design pattern, we solve problems like coupling the invoker of a request to a particular request. I mean, that coupling is avoided, and because it's not hardwired. And then it's like, if you remember in old times, or like there are devices where you have to go to the device and then press the button, which means like it's a hardwired thing. Whereas in a remote, like, I mean, you just press the button on the remote and it translates to the method which is within the device. So if you see this example, we have an invoker. Invoker is calling the command, and that command is actually executing and calling the action on the receiver. Right? So that's how it works. Invoker doesn't know about the action on the receiver, it knows about the command, and command translates into the action. Another behavioral design pattern which is very popular is the iterator. In the iterator, we can use it to traverse a container and access all the elements of a container. Like, I mean, if we have a collection like a queue, or if we have a like a some kind of a tree, so we can iterate through all the objects within that container. So there are like, different kind of algorithms, different kind of iterators. So the primary purpose is that iterator will decouple the algorithm from the container. Like container tree knows how to like organize the data within a tree, but tree doesn't know how to traverse it. But if you get an iterator, it knows that whether you want to go breadth first search in the tree or you want to depth first search in the tree. So you can use those kind of iterators to traverse the tree. The problems solved by iterator design pattern are like the elements of an aggregate object should be accessed and traversed without exposing its representation. So you don't need to know the representation of tree, you can just traverse it. Like if we have DOM parcel and then we have sex parcel, like then we can use that to just traverse it. And then we have a strategy design pattern. This is also a behavioral design pattern. In this design pattern, we enable selecting an algorithm at runtime. So like, I mean, instead of hardwiring the algorithm, at runtime, we can specify what strategy should be used. So the clients, they can specify what is the context, and based on that context, the specific algorithm will be picked up. So in this class, we have a context, and then we have strategy interface with some algorithm, and then we have strategy 1 or strategy 2. So these are two different strategies that have two different algorithms. Now when the client calls the algorithm, then it comes to know that, oh, now is the time to call strategy 1. So client calls the same method algorithm, but in reality behind the scene, because of the context, the right kind of strategy is picked, and that will be returned. So one example is like, I mean, if you have a shape kind of a class and you are calling a method calculate area. Now if client wants to call the this method of shape to calculate the area, then it has to specify what type of object is that. If it says the type is circle, then the area will go to the concrete implementation of circles area, which is pi r square. And if client says the type is square, then it will just go to r square, which is the side of a square. So that way the strategy is defined at the runtime based on the context. Alright, that's all on this topic of design patterns, and it is very good to know these patterns in detail, and we will have a series on this, and soon you'll be getting it. And if you want to have more questions on this, then put it in the comments. We'll be happy to answer that for you, and keep letting your feedback come to us. That way we can improve these videos, we can cover more topics that you are interested in. Thank you, and do like this video and share it with your friends so that they can also prepare well for interview.